Welcome to the course on two-dimensional signal processing, principles and practices. In this lecture, we will look at the two-dimensional discrete Fourier transform. So, the discrete Fourier series we had done in the previous lectures. The 2D discrete Fourier series, if we take it, the sequence x tilde of n1 comma n2, you can notice that tilde, which means that is periodic. So, the periodic sequence 2D, we had done e minus j 2 pi k n1 by n1 into e power minus j 2 pi k n2 by n2. This is summations varying from n1 and n2 are from 0 to n1 minus 1 and 0 to n2 minus 1. So, we get the frequency domain spectrum values here x tilde of k1 comma k2. So, this is the analysis equation, and the synthesis equation what we had is x tilde getting this sequence back from the coefficients, DFS coefficients. Here k1 is varying from 0 to n1 minus 1 and k2 is varying from 0 to n minus 1 summation. So, j2 by k1 n1 n2 n2 here. So, the scaling factor 1 by n1 n2 is added in the synthesis equation. So, using this 2D discrete Fourier series, we know that this x tilde is periodic as I said, and it is varying from samples n1 0 to n1 minus 1, 0 to n2 minus 1, and this is also periodic k tilde k1 comma k2, where k1 is varying from 0 to n1 minus 1 and k2 is also varying from 0 to n2 minus 1. So, this is periodic and this is also periodic in the case of discrete Fourier series. If we recall the discrete and periodic sequence, that periodic map into discrete and discrete would map into periodic. So, that is how we get both the discrete periodic as well as here in the frequency domain also the case of discrete and periodic. If we extend that idea of that 2D DFT, that what we had done in the 1D DFT from the 2D discrete Fourier series DFS, okay. So, we would get the 2D DFT from the 2D DFS. So, the frequency domain representation of the finite extended sequence. So, the previous equation is valid for the periodic sequence. Okay. So, then here now if we take the periodic sequence x tilde n1 comma n2 and multiply that with the function, that is a rectangular function of n1 comma n2, the dimension is n1 cross n2. It represents the rectangular function. This function is equal to 1 for varying n1 between 0 and n1 minus 1 and n2 between 0 and n2 minus 1. So, we have whatever this 0 to n1 minus 1 and n2 minus 1. So, these values will be, this is n1 and n2, these are values 1 defined for a particular n1 and n2. This is okay. So, rectangular function. So, rectangular 2D sequence which is having all the values 1 for a region of support and remaining values it is 0 all over here. So, that is from 0 to n1 minus 1 and 0 to n2 minus 1. So, if we multiply this for a particular periodic sequence, then we can get the sequence only for this region of support. That is what we have given x of n1 comma n2. So, that is making the finite sequence. It is not periodic sequence which is spread over the infinity. Here we get the finite sequence. So if we could multiply the periodic sequence with rectangular function to get the finite sequence in the time domain, what is the equivalent in the frequency domain? So, this is an example of x of n1 comma n2 which is periodic in the sense it is having this type of sequence. We can say it can be extended also in this direction and in this direction and this direction. So, that is periodic, and if we multiply by a rectangular sequence, here this is going to be 0 and it is spread over. So, we get a sequence 1 where this is a one pattern of it. So, just to extract one pattern of this x of n1 comma n2. So, with this we can get x tilde also back, or x of n, getting x of n from x tilde is multiplying by the rectangular function, or we can get this x of n from this, we can get the x tilde as well. So, x tilde can be obtained from x of n. So, it is invertible. Let us see that even how do we get the x tilde back. So, if you have x tilde, you can get it x of n, that is the previous case, and how if you have x of n, that is the one which is shown multiplied by the rectangular function, then that is a one pattern. That one pattern can be shifted in n1 and n2 with one varying from minus infinity to plus infinity, that is x of n1 n2 n1 minus n1 and n2 minus n2 depends on n1 and n2. That pattern will be repeating and in one direction, and similarly the other direction also can be. So this pattern can be one pattern and then shifted one this side, shifted one, and then the n2 side shifted can also be obtained from the x of n. So repeating that and then summing it over would give the periodic sequence which is spreading from minus infinity to plus infinity. So this is how x of n and x of tilde, x and x tilde can be obtained from one to another. So what about the DFS coefficients? So here the DFS coefficients, that Fourier series coefficients were x tilde k1 comma k2. If this is that from the coefficients of x tilde, this is in time domain. And if you know that, then how do we get what would be the DF truncated coefficient? So if this is x tilde and x tilde is truncated with r of n1 comma n2, you would get, if you apply the Fourier series, you would get x tilde would be xk, now x of k1 comma k2. Now if you have the Fourier series of this and multiplying again in the frequency domain with the rectangular function, which is also 1 for size n1 comma n2, we can get this x of k1 comma k2. So this DFS coefficients can give the finite one, and this finite one we can use it like this repetition and get back this in the frequency domain as well. So the Rn is defined as 1 for this region, similar to the time domain 1 or the space in 2D. This is the frequency domain k1 and k2. This is 1 for this region, k1 between 0 to n1 minus 1 and k2 0 to n2 minus 1 and 0 otherwise. If this is the case, this process is also invertible. So knowing this x of k1 and x of k2 and shifting it left and right with the r1 and r2 minus infinity to plus infinity and sum it over the coefficients, we can get the DFS for the periodic sequence. This is equivalent to periodic sequence. So from the sequence x of n1 comma n2, we can get the x tilde of n1 comma n2, or if you know the periodic sequence, multiplying this by the rectangular function, we can get back this x of n1 comma n2. From this x tilde periodic sequence, we apply the DFS, get the frequency domain coefficients, and from this frequency domain coefficients multiply by this r of k1 comma k2, and we can get x of k1 comma k2. If we know this k1 comma k2, we can get back this x tilde of k1 comma k2 also by multiplying this sequence with the and summing it over with in this fashion. So it's possible to go from one to another in both ways, that is finite sequence and its periodic, and then finite sequence in the frequency domain and its periodic one. So these are related with the Fourier series. So now the equation now of the DFT, that the finite sequence what we get from the DFS is the 2D DFT. So n1 varying from 0 to n1 minus 1 and n2 varying from 0 to n2 minus 1 summation x of n1 comma n2 e power minus j 2 pi k1 by n1 and 2 pi k2 by n2 minus this. Where k1 and k2 you can just now correlate that with the 1D DFT, where k was varying from 0 to n minus 1 and it is extended here to 2D, where k1 and k2 are varying from respective support regions here, and it is 0 for otherwise. So this is for the finite sequence. So how these are related with the Fourier series coefficient and the periodic sequence have been shown. And IDFT, this is the synthesis equation of the 2D DFT. So if we know the coefficients, multiply this e power j 2 pi k1 n1 by n1 and sum it over, and the scaling factor you can see is to get back the sequence here, the finite sequence, and it is 0 for otherwise. Now knowing the analysis and the synthesis equation, and we have also learned some of the properties, and this sequence x of n1 comma n2 is n1 cross n2 point sequence, and here as well as the frequency domain also x of k1 comma k2 for the same size n1 cross n2. And from the finite one, the region of support x of n1 comma n2 is 0 for outside this region. That should be noted, and this is for the first quadrant sequence. Okay, so support sequence is first quadrant. And if we relate this with the DSFT, that is what we have done 2D DSFT, that is x of omega 1 comma omega 2 or x of e power j omega 1 e power j omega 2 is obtained n1 summations varying from 0 to infinity. You can see that it is not stopped with a periodic value because it is for the aperiodic sequence. X of n1 comma n2 e power minus j omega 1 omega 2. This omega 1 and omega 2 are continuous in case of DSFT or the 1D DFT we had seen. So now if this omega 1 is replaced with 2 pi k by n, or 2 pi k1 by n and 2 pi k2 by n. So it is sampled. When you sample this omega for various values of k1, you get this is nothing but the DFT. So DFT is a sampled version of DTFT or the DSFT in case of 2D. So we have seen that samples. Now how do we compute this DFT? Okay, so the 2D DFT here, what we mean. So take a 2D sequence x of n1 comma n2 and which is 1 0 2 1. Okay, this is 0 0 and then 1 0 and here is 0 1 and 1 1. And similarly there is another sequence x of n1 comma n2 1 0 1 0. So we'll take the individual DFT and then we'll try to prove some of the properties here. So here the sequence, if we plot it in this case here, sorry, n1 and n2, this is 1 here. We know how to get the matrix from the plot and also the plot from the plot how to get the matrix. So this is 1 and 1 and here it is 0 0. It's not shown over here in these cases. This is 0 0. Okay. So this is a x and this is h. Now we'll get the DFT of this sequence. So the equation is given DFT equation, sorry, 2D DFT equation, and then where n1 up to 2 and n2 is also 2. So that's why this is varying from 0 to 1 and 0 to 1 in this given example. So 2 pi k1 n1 k2 n2. So now we can expand this for k1 and k2 also from 0 to n1 minus 1, 0 to n2 minus 1, 0 and 1. So k1 k2 values will be 0 and 1 only. So for 0 0, so if we compute, this becomes 1 and so we have to sum this samples whatever there 1 0 2 and 1 for x, for a signal x, and this would result in the 0 0 component is 4 like the DC what we obtain in the 1D. And in the case of second 1 0, k1 is 1 and k2 is 0. So we substitute here, the k2 term becomes 1 and this is in terms of e power minus j pi n1. So now vary this n1 and n2 0 0 0 1 1 0 1 1 and minus j pi also, get the value, this value is minus 2. Okay. And similarly for 0 1, k1 equal to 0 and k2 equal to 1. So getting this equation and getting the value of 2. So substituting here and get, and 1 1. So both vary, k1 equal to 1 and k2 equal to 1. This is not one bin index, we have the two bin indices k1 and k2. Okay. So both of them are varying from 0 to 1, 0 and 1, 0 1. So in this case 1 1 we get the value as 0. So the x can be obtained, x of k1 comma k2 what we got is 4 2 minus 2 and 0. So similarly we do the 2D DFT for the h, that is the second sequence. So if you get the h of n1 comma n2 e power minus j 2 pi k1 n1 and n2. So similar way we can vary this from k1 0 0 and 0 1 1 0 1 1. Okay, h, obtain this h of these things and we got the samples 3 1 minus 1 and 1. So both of the x and h are known. Then if you multiply this x and h, suppose in the frequency domain, what we obtain the coefficients, DFT coefficients, that is not the matrix multiplication. We should note down this is the point wise, I mean the element wise multiplication. So 4 into 3, this is 12, and 2 into 1, the corresponding positions are multiplied, minus 2 into minus 1, this is 0 and 1. Okay. So y of k1 comma k2 we get something. Okay. So that is 12 2 2 and 0. So, from the IDFT, y of n1 comma n2 is the coefficient y of k1 comma k2 what we have got here. Okay, we use this and find the inverse DFT now. So So j 2 pi k1 n1 k2 n2, this is the synthesis equation, and the scaling factor can be noted. These are 2 and 2, so it's 1 by 4. So we compute y of 0, 0. So n1 is also varying 0, 1, and n2 is also varying 0, 1. Okay, so this value, in this case, this n1 is between n1 minus 1 to 0, and n2 is between n2 minus 1 and 0. So if 0 and 1, so k1 varies from 0 to 1, and here also we get from the multiplied frequency domain coefficient, we get this 4. First one is 4, y of 0 comma 0, and y of 0 comma 1 is 3, and if you obtain y of 1 comma 0 is 3, and y of 1 comma 1 is 2. So we get it through the equations. So y of n1 comma n2, the sequence is 4, 3, 3 and 2. So what is this sequence, what we get from the frequency domain samples? So this is nothing but the circularly convolved sequence of x and h. Okay, so if you take x and h, this two-dimensional sequences x and h, and circularly convolve it, you would result in this sequence, that is y of n1 comma n2, which is also can be related with the DFT. This is also valid in the 1D DFT. In 2D DFT, the x, this k1 comma k2, that is 2D DFT of the first sequence and 2D DFT of the second sequence. 2D DFT of second sequence, multiplying them and taking the, that is the DFT of y. Okay, so that is DFT of the multiplied one, this coefficient, and compute the inverse DFT, that is 2D DFT. That would result in y of n1 comma n2, which is nothing but circular convolution of n2. Very important property of DFT can be obtained. So these are related in a circular convolution. So circular convolution, it's a multiplication in the frequency domain, x and h circularly convolved, sequence this y of n1 comma n2, and take the DFT of it, you would get y of k1 comma k2. This is equivalent to taking the DFT of this and multiplying the two coefficients. So this is how the time domain and frequency domain are related. So the circularly convolved sequences given the multiplication in the frequency domain. So this is called the circular convolution. Now using that, we can conclude it with the DFS and the case of DFT, how these are related. So x tilde and y tilde, these are periodic sequences. If you circularly convolve, the periodic convolution is resulting in the coefficients in the Fourier series and its multiplication. So here circular convolution is resulting in a multiplication. So how does it can be obtained for finite sequences, because this is periodic, and x tilde periodic convolution of y tilde and multiplying by a rectangular sequence in 2D n1 and n2, so give the finite sequence. Okay, so this finite sequences, if you just take it in the frequency domain, it is x tilde and y tilde are here. So this is multiplied here and this is multiplied here to get r square. R square is also nothing but r only, because one, all of them, the region is 1. So it's only represented r, n1 into n2 is k1 comma k2. So multiplying this y and x in the frequency domain and multiplying that with the r, which is equivalent to multiplying here also in the time domain. So that's a key here, x tilde r, and it's equal to, you get the finite sequence x of. So we have seen already this multiplication in the time domain on the, or in the frequency domain, that would result in a finite sequence. So this is for the x tilde, you get x, and similarly y tilde, you get y by rectangular function, because r square we had said already that is going to be resulting in r only. So we restricted with 1 r, not representing the r square. So the resultant would be finite x and finite y. So the circular convolution in circularly convolving two sequences in its time domain is multiplication in the frequency domain. That if it is a periodic sequence, we can also make this with the, multiply that with a rectangular function and make it finite sequence and convolve, which is equivalent to taking the finite sequences in frequency domain and its DFT. So circular convolution, this we had already, is a circular convolution is a multiplication in the frequency domain. That's what, without taking the R into consideration, these are obtained from, these equivalent to the previous argument. So now, how this linear and circular convolutions are related, we had seen in the 1D DFT and in case of linear convolution and circular convolution. So, under some condition, the result of circular convolution is identical to the linear convolution. If you recall the sequence having n1 and length, and then second sequence has a length of n2, then the linear convolution would result in n1 plus n2 minus 1. In case of circular convolution, n1 equal to n2. Okay, that is, so with this background, we will see the relation between this linear and circular convolution. So, suppose in a sequence, take the sequence f, which is 0 outside the region, okay, n1 dash and n2 dash, and g, there is another sequence is 0 outside the region, this, that means this has a region of support, one region of support, and g also one region of support. Then we circularly convolve these two sequences, that is equal to linear convolution when that is assumed periodicity is, this is having the n1 cross n2. Okay, so in this case, n1 should be greater than or equal to n1 dash plus n1 double dash minus 1, and n2 should be greater than or equal to n2 double dash and n2 dash minus 1. So when in the previous, in 1D case, we have seen this as n1 plus n2 minus 1. So when you perform the linear convolution, length will be equivalent to circular convolution when you make this circular convolution length n as this n1 plus n2 minus 1, at least of this. Greater than this, all would be resulting in values equal, that is circular and linear convolution results will be equal. So we would see with an example how this is going to be equal in the cases of that. So let us take a sequence f of n1 comma n2, which is having the length n1 dash. Okay, this n1 is n1 dash maximum, and n2 is n2 dash. The length, finite length is mentioned, and 1 1 1 this is having n1 dash and n2, and the rest of the region it is 0. And g is having similarly 1 2 here n1 double dash, because to represent it from different from this sequence, and this is n2 double dash. So this restriction on n2 is this, and restriction on n1 is this. So the first sequence is having n1 up to n1 dash and having n2 up to n2 dash, and the second sequence having n1 on n1 double dash and n2 on n2 double dash. So this is the sequence f, and the other sequence is g, n1 comma n2. So if we will see the convolution, linear convolution and the circular convolution here. So the length now n1 and n1 dash and n1 double dash are 2, n2 dash and n2 double dash are 2 in both the cases. That is weird. So the periodicity is 2. So if you linearly convolve it, so we have seen the example of linear convolution. How do we perform the linear convolution of the 2D sequences? That would result in 1, 3, 2, and here you can see that n1 and n2 different ways also. n1 dash and n1 double dash minus 1 equal to 3, n2 dash and n2 double dash minus 1 equal to 3. If we, this is with the case of linear convolution. Now if we take the same sequence f and circularly convolve it with the g, what we had. So this is representing the circular convolution, and we had seen in the previous lectures how do we do the circular convolution. Okay, so we have 1 1 1 and 1 2 3 4. If you do follow this procedure, would result in the sequence 6 7 8 9, that is n1 and n2. We get the length, you can see n1 direction 2 and n2 direction also 2. So there is no problem. So this circular convolution result and the linear convolution are not equal in this case, because this sequence what we had is, this is 2 by 2 and this is also 2 by 2 n1 and n2, 2 and 2 here. So now when that result would be equal, so the circular convolution result is n1 2 and n2 2 for the assumed periodicity. So now if this is for the circular convolution, both are different results, giving the result different results. But when this linear convolution, when make it n1 equal to 3 and n2 equal to 3, Okay, that is the sequence what we had, this f, and make this sequence which we have here also 0 1, and then here, so we have the other samples 0 again. Okay, so the other samples needs to assumed as 0, here also 0, here also 0. This is the 1 1 1 sequence if we have f here, f is 1 1 1. Okay, so the other 1 here, 2 and the 1 and 0, all 3, but other things should be 0. So n1 is taken as 3 and n2 is also taken as 3. So here extend this also to 0 0 and 0 0 0. So 3 by 3. So make n1 3 and n2 3 and then convolve it, in the as a circular convolution. So if you do the circular convolution, then the result would be equivalent to the f1g, which is the linear convolution result. As we got this, it would be the result of the linear convolution. So the assumed periodicity n1 equal to 3 and n2 equal to 3 at least, then the circular convolution result would be equivalent to the linear convolution. More than this, n1 greater than or equal to 3, n2 greater than or equal to 3, suppose 4 and 3 and 3 and 4 in the f and g. So if we extend that remaining with zeros, that's the sequence, this is 1 and 1, remaining can be extended up for any value of 0, that is depends on the periodicity we assume. That is, suppose n1 is 4, then we take it this 0 here 0 and up to this, these are all zeros. Okay, these are all taken to be zeros, this portion and this also, and here this also, all of them would be zeros. So extend this to 4 and n2 to 3, then convolve. Similarly the other one also, the g also, we make it like that, that is 1 2 and 3, these are the sequences of g, and we extend this as 0 and this is going to be 0 here, this is also 0 0 0 0. Okay, so in these cases, then we would have convolving it through circular convolution, which would also result in this linear convolution result, which will be also be greater than or equal to 0. That's what the condition says, that these two will be 0. But if for the cases less than that, less than 3 and 3, if it is 2 and 2, we have seen that it is giving a circular convolution gives a different result, and if it is 2 and this is 3, okay, so then or 3 and 2 also. So in that cases you won't be getting the linear convolution result as circular convolution, but when it is greater than or equal to both of them, then it would result in a value of linear convolution which is same as the circular convolution. So performing the y x f and g, extend and see that this result we obtain or not. So this is the case of circular convolution. So the case of 2D DFT, that is discrete Fourier transform, how can we obtain it to finite sequences? That is, this is applicable to finite sequences. So the periodic sequence, how can we reduce it to the finite extent sequence, or the region of support is finite? This x tilde, from that how do we get x? That is by truncating it using a rectangular function. So the rectangular function is assumed to be 1 for a region n1 cross n2. Then we can get it x from x tilde, or x tilde can be obtained from x by shifting this x and summing it over from minus infinity to plus infinity, we can get back the x tilde. So this is in the time domain. If in the case of frequency domain, so if we have the x tilde, and you can get the x tilde k in frequency domain, x tilde k, k1, k2, and multiply that with the rectangular function, that would give the finite x in k1 and k2. That's nothing but the 2D DFT. And if you know the x 2D DFT k1, k2, we can get back this x tilde k1, k2 as well by similarly shifting it in the frequency domain and summing it over the minus infinity to plus infinity. So these four components are related, and we can get one from the another from time to frequency domain. And this is also related, if it is a finite sequence, then we call the Fourier series, Fourier representation is the discrete Fourier transform. So how do we apply this 2D DFT? Through example we had seen, and the And what is the relation of the 2D DFT in the frequency domain of two sequences? If you multiply it, that is nothing but the circularly convolved sequence and taking that DFT of it. So that we had shown through an example. Also, what is the relation between linear convolution and the circular convolution in 2D? What is the condition in which? So if n1 and n2 are the two, n1 cross n2 and two dimensions, it should be at least the linear convolution should be equivalent to the circular convolution when n1 plus n2 minus 1 in one direction and n1 plus n2 in the other direction as well should be at least greater than n1 and n2. So that can be used for obtaining the circular and linear convolution results same. So the condition needs to be verified through an example which we had shown in this lecture. Thank you.